Welcome to the lecture series on GPU architectures and programming. So, in the last lecture we have discussed about this perceptron example for the NAND function, where we found that it is separable, and then the issue was that we are trying to identify what happens if we consider XOR as the function. And so, let us start from that example. So, if I consider XOR, so considering the truth table of XOR, so we have the positive output here, and this is the output corresponding to the other class. Now, as we can see that we cannot have a linear classifier for the XOR function, because it's fundamentally the function is not linearly separable, right. So, now this brings us the problem that how really are we going to tackle this issue. So, getting into the root cause of the problem, let's first identify that how really does this I mean binary classifiers where the functional form is linear, how really does it work. So, in general, if I consider any linear classifier, it is basically the equation of a line, right. So, I can simply write it is an equation of this kind of a form, so essentially this is this is the way we can capture any such linear classifier which is separating the function, separating the values, but as we see for XOR this is not possible. However, what about the other situations? As we have seen that for NAND it is definitely possible. So, if we just recollect what happens for NAND, so we will have positive outputs at all these points, essentially 0 0 0 1 1 0, and we will have the NAND function will evaluate to 0 only for the point 1 1, where AND evaluates to 1, right. So, that definitely can be classified by a linear classifier. So, this is linearly separable. Well, what about OR? We can just do a quick check and find out what happens with OR. So, for OR I have positive outputs here and here, that is 0 1 1 0 1 1, and here I have the negative output. So, this is also linearly separable, right. Now, in a similar way I can figure out what happens with AND also, and we can see that for each of these cases we can actually have a linear classifier, right. So, the next thing that we will try to do is we will try to figure out whether this kind of linear classifiers can help us to figure out how to handle the XOR function, which fundamentally is not linearly separable, right. So, for that let us see first whatever has been our linear classifiers, if I can express them in the form of perceptrons, since and that should be technically possible because they are linearly separable. So, this was our NAND function, right. So, since I have a line like this, I can check the corresponding, since this I will get a linear classifier, I can see that this will give me a line like this with suitable values of W1, W2 and B, and what will happen is we will have weights W1 and W2 as -1 here, and here I can get the output where I give an input of 1 and I have a multiply factor of -1.5. So, what we are trying to do here is creating a small perceptron corresponding to this NAND function, right. So, we are trying to see that since this NAND function has linear separability, I can express it in terms of this kind of an equation, and if I can express it in terms of that equation, I will have the value of W 1 and W 2 and B as like this -1 -1 -1.5, and then I can create a small perceptron like this, where x 1 gets multiplied by the weight -1, x 2 gets multiplied by the weight -1, and then I add the bias term, which is this constant 1 multiplied by the weightage of -1.5, and then if I am considering the output, I get the corresponding line which will have this kind of a feature, right. Now, similarly, I can just chalk out, well, for OR I can create a similar perceptron. So, let me just write it for OR. I will have a similar behavior with x 1, x 2 getting multiplied by these weights 1 and 1, and here we will add the bias constant 1 multiplied by the scaling factor 0.5, and we can easily check that this is going to act as our OR, right. Now, when we are talking about XOR, well, let us figure out first whether I can actually express it using this OR and NANDs. Actually, it should be possible. So, for XOR, as we know, I can actually write it as x 1 or x 2 and x 1 and x 2 bar. So, this is my OR, this is my NAND, and here I have AND. So, all these are kind of linearly separable, right. So, if we just break this down, I can have a representation like, of course, I mean you can just check that I can have this thing expressed like this. So, what it does is it gives me an idea that it may be possible for something which is not linearly separable to consider that, well, I have some intermediate neurons with whom I can actually create these values, right. But what I mean well, in this case for XOR I am able to create, and I am able to check that I can create a ANDed version of XOR using ANDing of OR and NANDs, where each of these OR and NANDs are linearly separable. But how does this work out in general? Can I say that for any such complex function which is not linearly separable, I can have linear combinations combining and creating such a value? Well, that is definitely not going to be true, right, because following our linear superposition principle, that is really not going to be possible, right. So, in general, I need a bit of nonlinearity in case I am trying to model sufficiently complex functions which are highly nonlinear. It has to be a combination of individual linear transformations, and they need to be combined with nonlinear functionals, right. So, we can say that, well, I am creating a version of of XOR where I am considering two linearly separable values, OR and NAND, and combining them with an AND. But in general, how does that work? So, the way we will look at it is, as we have been discussing, that we need a simple some kind of nonlinear function to be combining with linear components, and this is exactly what is done in a real perceptron, which forms the building block of a normal neural network. So, the way we do it is like this: you consider this kind of inputs x 1s and x 2s, which are marked here by these yellow nodes, and these inputs you are multiplying by weights W 1 and W 2. So, that gives you linear transformations, right. you can add the weights, I mean the bias here, the b values, I mean, so you put a constant and multiply by scaling factor like we have been doing for modeling NANDs and ORs, right. But then again what you have is those kind of linear expressions W1 x1 plus W2 x2 and similarly many more, and you can have some constants added through a proper bias, but that is not enough. We do not have any kind of nonlinear component here. So, fundamentally what we will do is, well, we will add a nonlinear transformation here which is known as the activation function. So, what we will do is we will have edges or synapses like this, right. So, these are my edges or synapses modeling the neurons synapses, they are kind of modeling the linear transformations, and then at these nodes we have neurons enabled with the corresponding activation functions. For example, here we have a picture of one activation function, right, and what we can observe here is this is a nonlinear function. All it is doing is taking the input and mapping the output corresponding to this kind of a functional map that is provided here. So, in this case as you can see that this is not a line, right. So, it is a nonlinear function. So, what we get here is let us call it as some sigma, and the final output is sigma composed with f, and f is the linear transformation. Now, of course, this the function we have here is not the only possible nonlinear activation function, there can be many others. So, when we say that this neuron fires, that means this function maps the input to the output, right. So, this example that we have here is for sigmoid, for which essentially the closed form expression is like this, y equal to 1 by 1 plus e to the power minus x. So, as you can see it has a 0 crossing at 0.5, so that is the input is 0, you get the output value as 0.5. Beyond that the function saturates to 1 and minus 1 as you go forward, right, sorry 1 and 0 as you go forward, right. So, of course, if you are putting the x value as very high, essentially this exponential term will decay and you get a 1. You put the x value as very low, as very high but negative, then again this will become very positive e to the power minus x. So, then again what you get is that y will come down to 0, right. So, the highest possible value is approximating 1 asymptotically, the lowest possible value is asymptotically reaching 0, and at 0 at x equal to 0 you have 0.5. So, that is the sigmoid function, and in general you can have other kind of nonlinear functions. For example, you can have this function which is the tan hyperbolic function, as you can see it is a different functional with respect to sigmoid. Here we have the closed form functional representation, and also as you can see that the value you are essentially having a central 0, and asymptotically with positive and negative values you are approaching 1 and minus 1 respectively. The other very commonly used activation function is ReLU or rectified linear unit. So, essentially it is just a max between 0 and the input value. So, if your input value is positive, that is what you get as output. So, that is approximate, that is kind of modeled by this linear this slope, right, and if your input value is negative, well you get a 0. So, that is why you have for all negative values you have a you are essentially on the x axis. So, these are commonly used activation functions in neurons. Again, what is the objective here? We are trying to model highly complex nonlinear relationships. The way we are doing it is we will create a neural network built using this kind of perceptron blocks, where the neuron is essentially modeling a nonlinear activation function, the inputs are modeling linear combinations with bias, and we are assuming that with this kind of combinations we should be able to suitably approximate any complex nonlinear function. And also as you can see, these functions satisfy some nice properties like differentiability, so that it helps you in computing the weights, something we will see how this kind of specific functional forms really help you. So, with this background, let us come to the generic structure of a multilayer perceptron or a feed forward network, right. So, what is the motivation behind this kind of multi-layer perceptron. As we have seen that there are functions which are definitely not linearly separable. We will like to combine them with suitable linear maps along with non-linearity, and eventually we will like to get the outputs, right. So, in that way, for modeling complex behaviors, we will have inputs going inside to neurons which are there in the hidden layer, and then they map the outputs to the output layer, and inside each layer you have neurons which are connecting with the inputs or the previous stage neurons, and whatever set of layers you have in the intermediate between the input and output layer, they are the hidden layers. And in deep neural networks, all that differs is you have significant depth in the hidden layers. How that helps is you are able to combine lot of linear and nonlinear activation functions in different possible ways, so that gives you the flexibility to capture many possible complex functional relationships, right. So, this is an example taken from a source called Welch Labs, which is in YouTube, and it provides a very nice example that suppose you are trying to create a correlation between hours spent studying and hours spent programming, along with what is the probability that you are going to pass or fail, right. You are trying to model this kind of a relationship. Well, this is just an example, there could have been many other examples. So, we are trying to propose a simple neural network architecture here. So, from the inputs you have these weights. So, since from a 2 input system you are mapping to a 3 neuron hidden layer, and as you can see this is like a fully connected system here. That means, every hidden layer neuron has its connection to all the inputs in the input layer, right. So, you just denote these connections by the weights W11 from x1 to f1, similarly W21 from x2 to f1, right, like this, then W22 from x2 to f2, W23 from x2 to f3, like this, right. So, here what you have is, after you get the values here from the synapses, where you get x1 multiplied by W11, you have the activation functions A1, A2, A3, like this, through which the outputs will pass once the neurons fire, and then you are again multiplying them by these weights, the output layer weights W11 prime, W12 prime, W21 prime, W22 prime, so on and so forth, to get into the output layer, where again you have this nodes denoted by G1, G2, like that, and finally, you have the output activation layer with nodes denoted by O1, O2, like that, right. So, this is a sample architecture for a classification system. So, essentially you are doing a 2 class classification, it is whether you are going to pass or whether you are going to fail, like that. And then what about regression? Well, like we discussed earlier, regression is basically about computing the continuous function, which is the approximation idea we have been talking about. So, that would mean at the output you have only one node in the output layer, and that gives you a value in a continuous range, right. Whereas, in classification you get values in all of this, and whatever is the maximum you will like to consider that as the the classification. Well, the definitions can vary as per your architecturals, right. But overall we can say that this is a generic structure for classification. We have multiple outputs and you are computing a real value here, and here you have only one output. So, that because you want a functional output, right. Now, what is the objective in our case? Again, we will try to focus on that. We are not going into the deep theory of neural networks and all that. Rather than that, we are trying to focus on what is the exact computation involved while training and testing a neural network, right. So, of course, we are not going to discuss core ML principles that need to be followed and all that. We are trying to consider that suppose I am given this network, my objective is to train the network, figure out, by training we mean figuring out these values of these weights given a test data set, so that we get a set of values which best approximates the functional relationship underlying the test data set, and how that computation can be accelerated by GPU architectures and all that. So, just doing a short summary here. So, for neural networks what we have is each network has you have a set of neurons, and each of these neurons of a layer, they accumulate the weighted sum of inputs from the previous layer, and then a neuron fires. That means it applies its activation function, and it will simply propagate the output of this activation function to the neurons of the next layer, right. So, essentially in that way we have a series of linear followed by nonlinear transformations going on the inputs and propagating finally to the output layer. Why is this necessary? Because as we discussed earlier, there in real life you have many complex functions which are not linearly separable. So, the way you will like to approximate them is through a combination of linear maps followed by nonlinear transformations and again linear maps like that, right. So, let us now come to the underlying computational parts here. So, let us consider this simple system of feed forward neural network forward propagation. Okay. So, let us see how things are going on here. So, we have this training example where the input is like this. So, you have a set of inputs like for x 1 you have these inputs like x 1 1, x 2 1. So, that is the first input pair. Again the second input, the second one you have is x 1 2 and x 2 2, and then the third one is x 1 3 and x 2 3, right. Now, so for this training examples, they are going to get multiplied by the weights. Now, as you can see, this is the weight collection. Essentially, it is a 3, you have a 3 cross 2 matrix, because you have weights W 1 1, because each of them are mapping to this like this, right. So, so as you can see, you have got 6 weight components, but how really are they arranged? So, for W 1 you have 3 components, because W 1 maps to the first neuron in the hidden layer, second, and W 1 2, W 1 also has a component mapping to the second neuron in the hidden layer, and similarly W 1 also has a component mapping to the third neuron in the hidden layer, right. So, these are the essentially the components of W 1, right. Similarly, you have 3 components for W 2, right. And then when you are considering the input, so for this x 1 and x 2 you have these training examples, right. Now, when you are getting this multiplied, you want the final value to be propagating to the hidden layer, right. So, like since x 1 has these components, right, you must the way this is arranged, that means for each of the values you are going to, for each of the training examples you are going to have values for this kind of tuples, right, and they are going to get multiplied with the corresponding components for the W's, right. So, this gets multiplied with this column, and similarly, right, for the next row you have it multiplied with the second column like that, and in that way you are going to get the corresponding entries. So, the first row and the first column multiply to give you the 1/1th entry here, right. So, that is what you get. So, x 1 1 multiplied by W 1 1 plus x 2 1 multiplied by W 2 1, and then you have the second x 1 2 multiplied by W 1 1. If I consider the next multiplication like the one I highlighted here, so this is going to give me, so the second row and second column, that is essentially going to give me this entry, right. So, x 1 2 multiplied by W 1 2 plus x 2 2 multiplied by W 2 2, right, and in that way I can easily figure out all these values that are slowly getting computed here. So, that is how using the training examples and the weights I can have these values propagating through the net towards the output layer. Of course, these values now will have to pass through the activation functions before they get mapped to the, before they get further multiplied by the weights and propagate to the output layer, right. So, let us see how that happens. So, here you have the inputs for the hidden layer, right. So, these are the inputs for the hidden layer, and here they get they need to be computed, right. So, you have this is the output here for the hidden layer, and then this hidden layer output gets mapped to the activation function some sigma, and when this activation function applies, out of that you are going to get a set of activations which we have denoted here like this A11, A12 like that, right. This is what we are trying to show is what happens after the activation functions get applied here. So, essentially as you can see that for A1 you will have this, next this, like that, so on and so forth. And then at the output layer you have this inputs coming out of the activation functions of the hidden layer. So, again let me repeat what we just did. So, we have these training examples getting multiplied by the weights, right. So, as you can see, since we are considering this two input system x1 and x2 and we have weights arranged like this. So, this is how one instance of the training examples will get propagated, right. Since the weights functionally form here a 3 cross 2 matrix, you multiply it like this to get components flowing through the entire chain, right. So, since you are going to have this since you are going to really have this kind of a setup that you have these many values propagating through the layers. So, at each point here you are receiving values like this. So, let us say for x11 it gets multiplied by W1, and then you have x21 getting multiplied by W21, and they are getting summed up here, and then after activation it is going to move on here, right. Similarly, if I look at the other points like x11 getting multiplied by W12, and I consider the other combination of x21 getting multiplied by W22 and it is getting received here. So, in that way I can say that each of these neurons they are receiving the different possible combinations, right. So, this guy is going to receive a combination of from x1 and x2 multiplied by W1 and W21, right. This is going to receive a combination from x1 and x2 multiplied by W12 and W22, right. And similarly, let us just take another example. This one is going to receive from x1 and x2 and it is getting multiplied by W13, and the other guy is getting multiplied by W23, right. So, similar, let us just consider one such example again. So, for x1, and of course, that is going to happen for all the different components of the values, right. That is also going to happen for all the different components of the values, and the components are like as we have for x1 we have 3 components, for x2 we have 3 components, and so on and so forth, right. So, for each of these components I will have this kind of combinations, right. So, for the first set of components I have the combination W11 W21, then W12 W22 W13 W23, and this is like what gets propagated in each of them, right. So, for the first activation function this is the part that is getting propagated, for the second activation function here this is the part that is getting propagated, and for the third activation function here this is the part that is really getting propagated. I hope that is clear from this, and that is really happening because we are also considering that the inputs they are in this kind of a vector form, right. Had it been something different, for example, if the inputs are scalar, that would be a different kind of computation. So, you have to really take that into account, right. For x1 and x2 both of them we are considering that well the inputs are arranged like this kind of size 3 vectors, right. x1 is a size 3 vector, x2 is a size 3 vector, and then for them I have this kind of values that are getting propagated. And after that, when these values are propagated, and then I have this entire thing flowing through the network, and then it is reaching these activation functions, and then the activation functions modify, they do suitable thresholding, and they will create the outputs. For example, for the first one I will get this A11, A21, like A31 it should be like that, A12, A22, so this one let me just correct it here. So, this should be A31, A32, A33 like that, right. So, once these activation values reach it, then what do we really have? So, these are the values that are flowing out of the network, right, and now they will get multiplied. So, this is what is coming and they now get multiplied by the output weights here, right. So, what are the output weights here? So, as you can see now, I have since here we are considering the regression example. So, everything is going to merge now, right. So, from the hidden layer to the output layer we have single connections and they are represented by W11 prime, W21 prime, W31 prime. 1 represents a single neuron and the output, and 1, 2, 3 the first index denotes the different elements in the hidden layer, right. So, here we have the hidden layer outputs, they are going to get multiplied by these weights of the synapses that they connect the hidden layer to the output neuron here, and then what we have is these vectors of A11, A12, A13, they are and A21, A22, A23 and so like this entire 3 cross 3 thing is getting multiplied with this corresponding weights here. So, essentially here what you have is a combination like this. So, what's really propagating? So, you have A11 multiplied by W11 prime plus A12 multiplied by W21 prime, A13 multiplied by W31 prime, these values. So, considering the first components, right, considering the first components that are coming out. So, that is what is coming out here, right. So, this is the first component, this is a set of first components that are coming out, right, for each of them. And so, here what we have is all the components. Now, from each of them whatever is the first component that would get to propagate through this network, and then you have at the output this kind of combinations. For example, what is the second element in the output layer? It should be A21 multiplied by W11 prime plus A22 multiplied by W22 prime, so on and so forth. So, if we just again mark it out. So, this and this will give you the first element, and similarly for the others. So, with this we have all the outputs flowing to the output neuron, where the corresponding activation function will now is now getting that is indicated here by the sigma, and you apply the sigma here. So, then you get the final output from the output layer, which will be again a vector of size 3. So, here again just to summarize, we are considering that we have inputs which are kind of 3 sized vectors. So, essentially we are trying to learn a relationship like this. So, x1, x2, so f of this So, we are trying to learn it like this, where this output is a vector of size 1 cross 3, and the inputs are all 1 cross 3s, right. So, that is the kind of a relationship we are trying to learn here, and accordingly the system is tuned. As you can see, for the input weights they are all having 3 components here, and for the output weights they are all having, since I am finally mapping to a single neuron, they are all having single weights here. So, we are not getting into further details of what is the motivation and all that. We are trying to cover it in simplistic terms, more in terms of what is the underlying matrix multiplication relationship that are going to happen here, right. So, with this we will end this lecture, and in the next lecture we will see how this really lends to the neural network training part, and how what are the underlying computations that need to be done for the training part. Thank you.